Hi. We are to take a multi-dimensional array and interchange the horizontally adjacent elements. Here is an example multi-dimensional array. It is a three-dimensional array with two layers, and each layer has two rows, and then we've got 5 columns. And our task here then is to interchange adjacent elements. So Griselda is being interchanged with Upton, they switch places. Prospero with Lycia, and then there isn't anybody to switch position with Topaza, so that just stays in place there. And the same goes for every row. And actually, note that we can really operate on individual rows. We don't have to worry about the overall shape of the array, though we'll get back to doing so anyway. So just to develop our algorithm, let's focus on just the first layer's first row, and then all the columns from there. We have those here. And so we'll start by defining or wrapping our anonymous function, defen, and we can take advantage of the partition enclose function to pair up these adjacent elements, and flip their positions, and merge everything back again. And the partition enclose function, it takes a for our purposes a mask of 1 when we are to start a new section, and then 0 when we are to continue a section. So we want a mask of 1 0 1 0 until the length of this vector. So we can get the length of the vector or the shape of it with the shape function of omega, and then we can use this to reshape 1 0. So we keep using from this array 1 0 cyclically until we have the shape that we asked for, and that gives us this mask. Then we can use that mask to partition the argument. And here we have the pairs that we're going to flip. And we now can reverse each one of these, and notice that the last one that only has one element, it's still a vector of character vectors here, but its reversal doesn't have any effect. And now all we need to do is merge these back together again. So we use a concatenation reduction, but the concatenation reduction has to reduce. It is a reduction, and it reduces then the rank, the number of dimensions, from 1. This is a list, a vector of vectors, to 0. So this is an enclosure of the actual vector result that we want, and we need to then disclose that to get the result we want. This took care of the simple case where it's just a vector, and we want this to apply to all the vectors that can be found as subarrays of our overall array. So we had the entire n here, and we can very simply do this. We just define our function here e for partition enclose, and specify that it should be applied on rank 1. So it's not really a specification, it's actually an operator that takes a function as left operand and a rank specification as right operand, and saying this function must never see any argument that has rank greater than 1. So in effect, the rank operator will iterate over our given argument and apply the function to every subarray of rank no more than 1, which is in fact always going to be present because the problem specification says that it will be a vector or higher rank array. So we can try this. Let's print out the names again just so we can compare them, and then we apply the e function to that, and we can see that we got exactly the result that we wanted. So this is one way to approach it, but there are many others. I'll go through another couple of another way we could do this is by indexing. So we could build up the indices of the elements reordered such that we get the result that we want. And that takes a little bit of an algorithm. So let's start again just by the vector case, and then we can apply rank 1 to get the full thing. So here's our vector. And again, let's define a lambda, a defen. And this time we have the shape of that. But now what we really want is to find out which order should we put them in order to sort them, but not just sort them by, say, alphabetically, but sort them such that we interchange adjacent elements. And we can start by generating the normal indices, right? So what we want here is the reordering, but we need to adjust our values because these are already sorted, so that 2 becomes less than 1, or 1 is greater than 2, and 3 becomes greater than 4, and so on. And we could do that by just adding 2 to every other element. So if we add 2 to 1, we get 3, and that doesn't clash with the next 3, because this 3 will also have 2 added to it and becomes 5, and it won't clash with the 5 because 5 becomes 7, and then the 2 and 4 stays. And then we just have to sort by that ordering, the ordering that would sort those numbers. Enough talk. And we can do this in exactly the same way as before. So we take the length and we use it to reshape. This time it's 2 and 0. And then we just need to add that to the indices that we computed over here. And for that, easiest thing is to make a little train, a fork. So we do the indices plus the reshaping of 2, 0, and we apply that whole thing to the shape of the argument. So we first compute the shape, and then we get the indices of the shape, and then we use the shape to reshape 2, 0, and then we add those together. They now have the same length, of course, and that gives us this. So we can see the 1 was incremented up to 3, and the 2 stays in place. The 3 became 5, 4 stays in place, and 5 became 7. Now we can grade this to find out what indices elements should we take in order to make this sorted. And so here we can see that we want the smallest element is the second one, that's the 2. Then the next one is the first one. The next one is the fourth one, and the next one is the third one, and then the fifth one. And that effectively gives us these flip pairs for indices: 2, 1, then 4, 3, and then 5. All that remains now is to use these indices to index into the argument, and we have gotten our reordering as we wanted. So here we're using indexing with grading. We can call this I, and then specify that this goes on vectors, and that means that we can let's print out our example names here again, and then we apply our function, and we can see again that we have the correct flipping of pairs. And finally, I want to show how to do this using the stencil operator. A stencil operator is normally associated with cellular automatons, game of life, things like this. It processes windows of an array. It's almost an edge case that it can have windows of size 2, and the window moves over by 2 steps, and that effectively isolates adjacent pairs. This time, let's do it testedly, and we can start with the first layer's first row. So we use round parentheses instead for a train or a tested function, and we start with a stencil operator, and then the idea here is that we use windows of size 2 with a movement also of size 2. So we need to make this into a matrix because every row serves a different purpose in the right operand stencil. The first row specifies the window size, the second row specifies the window movement. If there were additional dimensions we were traveling along, then we would have additional columns in this table. And we can isolate these, so we can the operand function to stencil is given 2 arguments, and we don't need the left argument, so we use the right function and then we enclose that. And we can see that we got the pairs, but stencil cuts the argument short if it can't complete a window with a specified movement. So we will have to address that. But for now, we don't have to necessarily enclose this. We could also increase the rank by not enclosing. So that gives us this table, and that can conveniently be reversed. And then we can ravel it again. Right there. Now, there is missing something, and that is the last column. So we can re-add that column, but of course this only happens when the rows have an odd length. So here we use a right reduction to get the rightmost element, and that adds this back again. If we had an even number of elements, then our code here would add one more column that didn't need to be added. So we can do this by cutting short our argument to just 4, not 5 names, and we can see that we have an extra delicia over here because that was the last element before it was moved one step to the left. This is of course wrong, but we can counteract this by taking the shape. So we take using the original shape, and that ensures that we chop off the excessive element if it exists. And then if we use the odd numbers here, 5, then we also get the right result. So this works again on rank 1, and we can call this S for stencil, and we can try to apply that on our whole multidimensional array, and we get the desired result. It would be interesting to do a speed comparison of these 3 approaches. So let's copy in the compare execution facility from the defense workspace. And then I also have a larger, here we only have 20 names, but I have a larger many-dimensional array called A. We can see that A has 20,000 elements instead of just 20, and it's distributed over 5 dimensions, so it's a relatively large array. And well, we can also look at the whole shape of this. It has an odd length and long last axis where we're going to do all the actual computation. So, and we're going to compare the execution, and we've got E with A as argument, and we've got I with A as argument, and we've got S with A as argument. And then we let it run for a little bit to see how they stack up against each other. And well, those are some significant differences we can see. And if we reason about it, we can also see why that is. And the stencil operator is optimized for certain cases, but not for what we're doing here. And so it goes in and actually applies a function to every window and moves around, and that is expensive to do. The partition enclose function generates an intermediary further nested array that isn't otherwise necessary. And the indexing just directly goes in and computes how we want the result reordered, and that then ends up being significantly faster than other approaches. But that said, we can do this much better. Because if we look at our definition, say we look at S here, we are treating every row separately, and potentially there are a lot of rows. And even though rank is optimized again for certain primitives and constructs, and when we have a complex function like this, there's nothing the interpreter can do, and it just has to loop through all the rows individually. If we could treat the whole array and in one go, then that would give us a significant speed up. And this is what array programming languages like APL are really good at. So let's try to reformulate this S into a function where we do not need to specify that the rank of the argument is restricted to 1. And here, well, we still kind of want to do that, but we don't have to do it on the entire function, because we do want these windows and on rank 1, but we can do that all the way in here instead. So this takes care of the reordering of individual rows. Then we might be missing a column. We add the rightmost column, so to say, that's the last element of every row in the entire array, to this potentially multi-dimensional array that comes out after running on rank 1. And instead of doing this take operation on every row individually, we take the shape of the original array, the multi-dimensional array, and restrict it along all axes, which won't have changed except for the last one potentially. So that's just one operation to cut short in our array. And now we can try to compare our original S with our S2 and see if that made a difference. So we can see that that became somewhat faster. It still doesn't get rid of this loop of the rank 1. We could potentially get rid of this one as well by specifying a window size that is 1 and a movement of 1 in every dimension except for the last one, where we have a window size and movement of 2. But it becomes a lot of computation to get that window size right and to then reform the argument back again to the original. So let's leave that there, because as we can see up here, the stencil approach is anyway much slower than the other one. So this will be more interesting with our other approaches. So then we had our function e, and let's try to define a new e2 that does this on the whole array instead. So we want to get rid of the rank 1 here. Now this gives us the shape of the entire array, but we only want the trailing element of the shape, which is the number of columns, so the lengths of the rows, and we can get that, for example, like this, to do with get the last element, the rightmost of the shape. Then we reshape to the mask that we want, and actually this works out very nicely, because by default the partition enclose works along the trailing axis. So this is going to split up our array into, should we say, vertical slices of width 2, and so everything else just works out. We reverse these 2-column and multidimensional subarrays, and then we join them all together adjacent to each other, and since we use the reduction to do that, we disclose, so this should just work out. So now let's try to compare E and E2. And we can see that just this little bit of modification gave us some very significant savings. Okay, let's see if we can do this with the I function as well. So we want to have a new I2 function, and we don't want to apply rank here. Now, we end up in trouble immediately because the square bracket indexing requires us to know the rank of what we're indexing. So we have to replace it with something else. And for that, there's actually, if you take these two square brackets and we merge them together, then they become the squad function, which is then a proper function indexing. But again, we don't really want to generate the indices along every dimension for all our elements. So we can use the slightly unpleasant looking square bracket axis to say that all the indexing that we are going to do along the last axis. So that is the same thing as the rank of the argument. And now, what we're indexing is on the left, but it normally takes it on the right, so we swap that. And in order to just reorder, so to have multiple indices along the same axis, then we need to enclose the argument over here. And then, of course, this is the entire shape. So just as before, we want to get the length of the last dimension, and the rest should stay the same. We get the mask, we do the grade, and then we apply that there. So now we can compare, and remember that I was the fastest one before, and now we're doing I versus I2, where we're not going over the individual rows with the rank operator. We are treating the entire array at once, and we get, well, similar savings as we did with E. But wait, there's more. Let's think a bit about these indices that we generated with the grade. Let's do it for 5 and for 6. We were thinking about this transformation as a positional one, flipping pairs. But actually we can think about it as a mathematical one. Originally we had 1, 2, 3, 4, 5, 6. And in order to get the 1 into a 2, we just need to increment it. And the 2 becomes a 1 by decrementing. The 3 becomes 4 by incrementing, and the 4 becomes 3 by decrementing. So instead of adding 2, 0, 2, 0, if we add 1 and negative 1, that pretty much gives us the result that we're looking for. The only exception is when we have an odd length. Here, the last element becomes too big. But we know that the last element can be no larger than the limit of this series. So we can clamp it using a minimum, and we don't even need to do a minimum on all the elements. We can do it just on that very last element, because we know that's the only one that can be too large. And with that in mind, let's go and change this I2 into an I3. Now we need to give this a name. Let's call it L for last, and change the changes into 1 and negative 1 instead of 2 and 0. We don't need to grade anymore, but we do need to clamp the last element. And with that, we can try running I2 against I3. Although, even though A has a lot of elements, the last axis, that's the important one, is quite short. So we don't see a whole lot of speed up here. If, however, we make B be a flattened A, such that there are 20,000 elements along that last axis that actually matters, then if we try comparing the performance when we now need to grade 20,000 elements instead of just 600 and something, we get a substantial performance benefit. So sometimes rethinking how we construct our indices and doing it in a less costly way can make a big difference. Thank you for watching.